Hi, my name is Joseph Bauer, and I'm the first author on this publication. I received my doctorate in biochemistry at the University of Akron. And the reason I mention this is because when I was a graduate student at the University of Akron, that's when I came up with the idea to synthesize nitrosylcobalamin, which is a analog of cobalamin, otherwise known as B12. It was interesting that a few years earlier, when I was in undergrad, um, taking biochemistry, a course taught by Dr. Mike Dunphy, who's also one of the co-authors on this manuscript, that's the first time I saw the beautiful structure of vitamin B12. And it had a cobalt center, and it was complex, and it was since that was an inorganic metal, those are also the chemistry of color based on the oxidation states. So it was a very beautiful compound. Cyanocobalamin, hydroxycobalamin, nitrosylcobalamin, they all have different colors: wine colored, reddish color, orange color. Cobalt, I believe, in the +1 state is brown, and the cobalt zero state is white. So it's very interesting for that chemistry. And so then when I got to the University of Akron, I joined the laboratory of Dr. Daniel J. Smith. That was a nitric oxide lab. And then receiving some training in advanced inorganic chemistry from Dr. Wiley Youngs, I was able to put all the pieces of this puzzle together and actually, in my mind, um, figure out a synthetic pathway to produce nitrosylcobalamin. And since that time, which was the late 90s, there's been over 25 publications on nitrosylcobalamin. We actually started a company, raised some funds. We had a pre-investigational new drug application, which was successful, but then we ran out of funds. And so what our hope is that this manuscript, this publication, is going to actually revive or revitalize our pursuit to get nitrosylcobalamin into the clinic to help patients. Now, this is a study which is very near and dear to my heart. My father died of glioblastoma, was treated, of course, surgically with radiation, temozolomide, and succumbed within several months of that of those procedures. You know, this has been around for a long time. Brain cancer, the treatment of brain cancer, in the late 1800s, early 1900s, some of the first surgical. Dr. Cushing's and others had done surgical procedures to remove brain cancers. In the 1950s, late 1950s, came about radiation treatment for these. And then temozolomide came about in, I believe, 1999. And then the combination of temozolomide with radiation with surgery was in the early 2000s. The shame of it is that standard of care has not really improved for over 120 years. The response rates, 5-year survival rates with patients with GBM are between 5 and 7%. And the median survival is about 12 to 15 months, even with all those interventions. So this is definitely an unmet need. If you look in the pipeline for GBM, there are a lot of things coming, but again, it's very difficult to get some of these approvals based on our current FDA approval process. But this was a very exciting study. I'm very thankful to be published in Oncoscience. Oncoscience is a true free open access publication. They don't charge you to publish in Oncoscience, and hopefully this is going to be a model by which other journals are going to adopt. But very, very proud to be in this journal. Had a wonderful reviewers and editors, very good suggestions that actually improved the presentation of the study. I know for sure one of the figures I think I had, it was like 2 figures combined in one. It was very confusing. But you know, when you're writing a manuscript, you don't often see that. But one of the reviewers pointed this out. I'm like, boy, that's a great suggestion. So we took that into consideration, and this paper that was published actually was much, much better from a presentation standpoint. And we also made some clarifications than when we submitted it. And that's basically the purpose of working with a scientific journal in a peer review context, working with the editor, and hopefully presenting the most transparent and straightforward science. One of the things that we learned, we knew that vitamin B12 crossed the blood-brain barrier, but we wanted to make sure that nitrosylcobalamin crossed the blood-brain barrier. A lot of studies that Dr. Cecil has done, which was published in some other journals, look at CD320, which is the B12 receptor on the surface of cancer cells. And so we were actually able to see that in human cancer cells and feline and canine cancer cells, that there was an expression of this receptor on the cell surface. And then again, that would be a justification of using a B12 related therapy to target tumor cells, and in this context, brain cells, brain tumor cells, glioblastoma. I want to thank the collaborators on this study. Of course, Dr. Annette Cecil and Dr. Michael Dunphy, my co-authors here, really helped in terms of the presentation and making it more concise and better transition between paragraphs, and really improve the writing. And then we, of course, work together to make sure that the statistics and the conclusions were representative of the actual data that we had. So we wanted to make sure we had a very transparent assessment of the effects of nitrosylcobalamin. Again, the purpose of this study was really to see if the nitrosylcobalamin crossed the blood-brain barrier and penetrated the glioblastoma multiforme, the tumor itself. And this work was done in the laboratory of Dr. Michael Vogelbaum, who's now at the Moffitt Cancer Center. His laboratory, he is a neurosurgeon. He was an expert in this rat xenograft, where it was a stereotactical inoculation of the U87 human glioblastoma multiforme cell line. And of course, I want to thank Dr. Daniel Linder of the Cleveland Clinic Taussig Cancer Center, because his laboratory and the Center for Drug Discovery and Development, which is now Translational Hematology Oncology Research, is responsible for adopting the National Cancer Institute's Developmental Therapeutics Program, SRB assay, which is a proliferative, anti-proliferative assay to screen compounds. And in actuality, Dr. Linder, Dan, his laboratory was the first to assess nitrosylcobalamin for anti-tumor activity. So I always would be thankful and grateful for that. So thank you, Dan. So now let's talk about the first figure from the Oncoscience. This, again, is part of the NCI 60, which is NCI 60 Developmental Therapeutics Program. They have 60 tumor cell lines. And if you look at it, the central nervous system is pretty much right in the middle there. It's not the most sensitive to NO-Cbl, but it's not the most resistant either. And you can look at the x-axis, talks about the average ID50. That is the dosage by which 50% of tumor growth is inhibited. And so when you look at an ID50, that is a way you can make comparisons of a drug across different tumor types. So for instance, the ID50 of leukemia is 6.5 micromolar, whereas the ID50 of breast cancer, is, at least in the screen, is 18.2 micromolar. So the leukemias are much more sensitive to the anti-tumor effects of the drug than, say, the breast cancer. But we submitted this compound to NCI. They accepted the compound, and it was their laboratories that did this testing. But it gave us hope because we were able to see that the CNS actually responded very well to the anti-proliferative effects of NO-Cbl. Now, if we go to this next slide, this is figure 2 from the Oncoscience publication. And the take-home message here is really we want to make sure that the NO-Cbl or nitrosylcobalamin accumulates in brain tumor more than it does normal brain tissue, because any sort of chemotherapeutic drug, you want to have a good therapeutic window. So which is the toxicity towards the tumor is much, much greater than any sort of toxicity towards normal tissue. And if you look at this particular, we gave 3 doses actually, 50, 100, 150 milligrams per kilogram to the rats at 2 time points, a half an hour and 24 hours. The beauty here is if you look at the brain tumor in the light blue, and you compare that to the brain in the green, you can definitely see 6 to 14-fold higher levels of NO-Cbl in the brain tumor than normal brain tissue. We also looked at the liver and the kidney because we know that in the liver and kidney, they're both storage depots for B12 type compounds, which NO-Cbl is a B12 type compound. And the kidney also will excrete B12. And we wanted to basically look systemically at that in those, what organs does it go to, NO-Cbl, and of course, you would expect it in the liver and kidney. Take-home message here, though, is of those systemic doses that were given intraperitoneally, the highest amount of NO-Cbl was in the glioblastoma multiforme, not normal brain tissue. The third figure from the Oncoscience publication looks at systemic exposure, meaning when you give the compound intraperitoneally, it goes through the bloodstream, what can you detect? And we can see that there are 2 ways to detect NO-Cbl. One is by looking at the nitric oxide component, so that would be serum NO, and the other would be looking at the cobalamin component, because again, NO-Cbl is a B12 derivative. And so we used an assay that looked at B12, but in this case, it was NO-Cbl. And you can definitely see at 30 minutes, there was a definite increase above baseline, which was sustained right at a little bit above baseline, especially at the higher dose of 150 milligrams per kilogram. Cerebrospinal fluid had a minor spike, but not really much more than you would have in the bloodstream. But the beauty here is we can actually track NO-Cbl, if you will, in the bloodstream, and maybe use that as a marker. Especially we can use it for pharmacokinetic analysis in the treatment of any cancer, but in this case, GBM. And so the last figure, figure 4, looks at NO-Cbl and traditional chemotherapy, in this case, temozolomide. Trail is part of the TNF-alpha superfamily. Trail itself did not really pan out in terms of a treatment for glioblastoma. There was too much resistance there. The half-life wasn't long enough, different factors, but primarily we wanted to see what would NO-Cbl do with 2 different chemotherapeutic agents that have different mechanisms of how they act, and will they work together to kill the tumor, or will they work against each other? And that's something we wanted to examine. But in both cases, if you look at panel A, that's looking at a combination of NO-Cbl and trail and U87 cells. Panel B is looking at combination of NO-Cbl and temozolomide in D54 cells. And you can definitely see that the combination of both of those agents resulted in synergy, which you can see in panel C and D, which is the Chow and Talalay synergy analysis. Any combination where the value numerically is below 1 is considered synergy, whereas if it's above 1, it's considered antagonism. But in this case, we were able to show synergy, and so that was a good takeaway. It helped with our hypothesis that NO-Cbl, we've done some previous studies that NO-Cbl will actually inhibit NF-kappa B, and it will inhibit its survival pathways. And so therefore, we knew that that mechanism of action was there, and temozolomide has been known to activate NF-kappa B. So we were hoping, that was our hypothesis, would this actually work? And it did. To once again thank the co-authors, Dr. Annette Cecil and Dr. Mike Dunphy, with their help in preparing the manuscript. I want to thank Dr. Michael Vogelbaum for his laboratory doing the xenograft studies in rats to help us show that nitrosylcobalamin does in fact cross the blood-brain barrier and preferentially is found in glioblastoma and not normal brain tissues. We also were able to look at the systemic effects of NO-Cbl in terms of, can we find it in the bloodstream? Would that be appropriate to do pharmacokinetics? And that was shown as well. I want to thank Dr. Daniel Linder in his laboratory, because he was the first actually to screen NO-Cbl in a SRB assay and was very helpful in terms of advancing and promoting NO-Cbl. I'd like to thank Dr. Daniel J. Smith from the University of Akron, because that is the nitric oxide lab that I received my training. And without that training, I would not have been able to produce nitrosylcobalamin. I did not have the synthetic skill set, which I was able to pick up after 5 years in graduate school. I'd like to thank Dr. Beller Setherum, who is a B12 expert in terms of the biology and functioning of B12, and he supported our group. And also I learned a lot from him, and Dr. Harry Hogenkamp from the Mayo Clinic, actually University of Minnesota, but he worked with Doug Collins at Mayo Clinic. And they were the first to look at radioactive or radio-labeled vitamin B12 analogs, and those analogs actually were detected by SPECT imaging in central nervous system tissues. And so that was some of the background that led to this particular evaluation of NO-Cbl in glioblastoma. Finally, I want to acknowledge my father, Joseph Fred Bauer, who courageously fought this disease, but sadly succumbed to it. But our hope is we can take what we have here and utilize it in the clinic, and hopefully we can extend the overall survival for these patients in a non-toxic way. So I thank everyone who's watched this today, and I thank Oncoscience again for the editorial team, publication team, and the overall philosophy of providing a free platform to promote oncology. Thank you.